Very good morning to all the students. I'm Dr. HimaBindhu and I'm here to teach you the robotics subject. And my today's topic is feedback components. As in the earlier session, we have seen what is the use of a feedback component and what are the different types of feedback components. So in today's session, we will be studying about one of the feedback component, which is called an encoder. What do we mean by encoder? What is the use? As I've told you, we have seen the different types of feedback components, right? That is position sensor and encoders. So generally, position sensor is used to determine the position and orientation of the robot. So here, this particular position sensor was being divided into two types, that is potentiometer and resolver. Right? The robotic component is, the feedback component is one of the very important and crucial component which is used to operate the precise control of the robot system. Right, a feedback component is one of the most important component which is used to operate the precise control of the robotic system. So that is the reason why these feedback controls have come into action, and we are utilizing this in the robot component. In the previous session, we have studied about the position sensor, and we have studied about the potentiometer, and in today's session we will be studying about encoder. What do we mean by encoder? What is encoder? Generally, encoder is a optical device. Right? Encoder is a optical device which converts the motion into sequence of digital pulses. Right? An encoder is an optical device, that is, here you can see this, right? It is an optical device which converts the rotary motion into the signal pulses, right? Into the signal pulses. So here the encoder is again being divided into two types, that is absolute optical encoder and incremental optical encoder, right? The encoder is being divided into two types, that is absolute optical encoder and increment optical encoder. Now, there is a variation in these two encoders. What is that difference we will be seeing? So here, generally, the absolute optical encoder is nothing but it consists of n number of concentric rings. Right? These are the concentric rings. So this particular optical encoder consists of a number of concentric rings, and when this particular encoder is being placed on the shaft of the robot, for example, this is the shaft of the robot, right? For example, this is the shaft of the robot, and to this particular shaft of the robot, we are placing an encoder, right? To this particular for this particular shaft, we are placing the absolute optical encoder in this particular form. And as the shaft is rotating, the encoder also gradually rotates, right? As the shaft is rotating, the encoder also drastically rotates. Now, this particular encoder is having few lights, right? Here, as you can see, this particular encoder is being filled up with some dark portion, and the remaining portion is left over through which the photo signal, the light source, can pass. In the same way, here in the second concentric circle, this is the dark portion which is being filled up, right? And this is the remaining portion is being left empty. Right, this is the dark portion, remaining portion is being left empty. In the same way, like that, for various concentric circles, we have few dark portions and we have few portion which is left off through which the light source can be passed. For example, you can see in this figure. Here in this particular place, we have the light source being placed, and this is the shaft, right? This is the shaft on which we are placing the concentric encoder, right? On which we are placing the concentric encoder. Now, as the light source is being passing through this particular optical encoder space, if for example, this is dark, it will give you a zero signal, right? For example, if this particular area is dark, it will be giving you a zero binary code. And then as it is rotating, it will pass, the light source will be falling on this particular place. And again, if this particular place is also dark, again the binary code given will be 0. Right? Again, when it is rotating, the light signal falls in this particular area. And if this particular area is light, right, through which the light source can pass, it will give you a binary code of 1. Whenever there is the light source passing through the encoder space, the binary code given will be in the form of 1. And whenever there is no light source being passing, the binary code will be given as 0. In the same way, when it is rotating, again when the light source is falling on this particular space and it is dark, it will again give you a binary code as 0. As we can see, this particular first concentric circle is being called as 2 power 0, right? This particular concentric circle is called as 2 power 0. The second concentric circle is called as 2 power 1. The third concentric circle is called as 2 power 2, and the fourth concentric circle is being called as 2 power 3. Right? In the same way here, this is the concentric circle which is being placed on the shaft. Right? So, as the shaft is rotating and as the concentric circle is rotating with respect to the difference here, the light source passing through the concentric circle will give you a binary value as 1, and the light source which is not passing through the concentric circle is being given with the binary code of 0. So here the first portion whatever we are seeing is nothing but 2 0. So for 2 power 0, if the light source is not passing, it is 0. So for 2 power 1, if the light source is not passing, it is again 0. For 2 power 2, if the light source is passing, it is taken as 1. For 2 power 3, if the light source is not passing, it is being taken as 0. So, when we are taking this particular binary portion, for example, for 2 0, 2 1, 2 power 2 and 2 power 3, if the values are given in this particular form, then this particular binary code's divisional value, this particular binary code's deviation value will be calculated as 2 power 0 into 0 plus 2 power 1 into 0 plus 2 power 2 into 1 plus 2 power 3 into 0. So what is the value given? 2 into 0, 0 plus 0 plus 2 2s are 4 plus 0. So what is the value? It is nothing but 4. In the same way, if we have 1 0 1 0 for this, what will the value become? 2 power 0 into 1 plus 0 plus 2 power 2 into 1 plus 0. So what is the value? 2 plus 4. The deviation value will become 6. In the same way, if the value is taken as 1 1 1, so deviation value will become 16. So this is how we calculate the angle. This is how we calculate the angle of the robot. So here, when we need to calculate any particular angular displacement of the robot's manipulator, we will be selecting the encoder, and in that the absolute optical encoder is one of the complex type of the encoder, as the construction of this particular type of the encoder is complex because it consists of n number of concentric circles, and as we consider as one particular encoder is costlier, and when we are taking n number of concentric encoders, it is this particular type of the encoder is costing more, right? It is costing more. So generally this particular type of the encoder is not much frequently used, as it is not much frequently used as it is costly, and its construction is complex, and its construction is complex, right? So this particular type of the encoder is complex in construction and is costly as it has a number of concentric circle and it is complex to design. Right. So this is being mounted on the shaft to which is nothing but a rotary device, and this particular type of the absolute encoder is used to generate the digital world identity, actual position of the shaft measuring from zero position, that is digital is nothing but the in this particular form, and it is used to measure the angular displacement of the particular shaft which is rotating. For example, this is the shaft, right? This is the shaft, and to this particular shaft we have, this is the optical encoder being placed, right? This is the shaft, and to this particular shaft we have the optical encoder being placed. Now to this optical encoder, this is the dark portion, this is the lighter portion. Right, this is the dark portion, and again this is the lighter portion. All this is dark portion and this is the lighter portion. When the light source is at some position and it is striking this particular dark position, it will give you a binary as 0. And when the light, so when this is rotating, when the light source is passing through this particular space, it will give you a binary code as 1. And again, when it is passing through this light source, it is giving you a binary as 1. And again, to the dark source, it is giving you a binary of 0. So how do you calculate this? 0 plus 2 power 1 into 1 plus 2 power 2 into 1 plus 0. What will this value be? 2 plus 4, which is nothing but 5. So the deviation value will be 5 as per the binary value. This is how we write the binary code. Clear? So now this is rotating in 360 degrees angle. Right? This particular encoder is rotating at an angle of 360 degrees. So when this particular code is rotating at an angle of 360 degrees, we take the angular displacement as 1 by 2 power n condition. Right? 1 by 2 power n condition. That is, n is nothing but number of concentric circles. If we are having 10 number of concentric circles, what will the value become? 1 by For example, we have 360 degrees angle. This will be taken as 1 by 2 power n. When we have 10 concentric circles, what will the value become? 1 by 1000, which is nothing but 0.36. So this particular 0.36 is the angle of the shaft at which it is rotating. This 0.36 is the angle of the shaft which is rotating. Clear? So this is how we calculate the angular displacement using the absolute encoder, right? So this particular angular displacement, as I've told you, is very complex, and since it is complex, it is cost effective, right? Next, moving on to the incremental optical encoder. Now, when we come to the incremental optical encoder, this type of the encoder is most frequently used feedback robot, and it is less expensive, right? It is most frequently used rather than the absolute optical encoder. The incremental optical encoder is most frequently used and it is less expensive compared to that of the absolute optical encoder. Why? Why is it less expensive and why is it most, since it is less expensive only, it is used frequently. But why it is less expensive, we need to identify. There in the optical encoder, we have n number of concentric circles. Yes, there in the optical encoder, we have n number of concentric circles, due to which the construction is becoming costly, complex, and it is costlier. Whereas in the incremental optical encoder, it has only one concentric circle. Right? The incremental optical encoder has only one concentric circle, and to that particular concentric circle itself, we are placing two light sources, photodetectors. Right? We are placing two photodetectors. To this particular concentric circle itself, we are placing two photodetectors which are fixed. One photodetector is called as A and the other photodetector is being called as B. And this particular concentric circle is rotating in a clockwise direction. Now, with the help of the incremental optical encoder, we can even identify the direction of rotation of the shaft, in which direction is it rotating, whether it is rotating in the clockwise direction or whether it is rotating in the anti-clockwise direction, with the help of this particular signal simulation. Right? Here, one of the advantage of the incremental optical encoder is that we can identify in which direction the rotor or the shaft is being rotating, whether it is in the clockwise or whether it is in the anti-clockwise. That depends upon the output result which we are getting. That is nothing but the signal processing. That is, it is nothing but with the help of the signal pulses. And as I've said, it is simple in construction, it is less expensive, it is used to determine the angular displacement, right? And it consists of only one port disc, and it consists of two photo detectors. And this particular, here we calculate the angle by counting the number of dark circles and light circles, right? By counting the number of dark circles and the light zones, the angular displacement is being measured with respect to the starting position. So here, when this particular shaft is rotating, here this particular photo detector initially is, for example, this particular photo detector is at this place. So initially the light zone which is covering is this particular area. So here it is giving you the signal in this particular form, which is nothing but the light zone. Next, it is traveling to the darker zone, where this is the darker zone distance and it is giving you the darker door distance. Again, it is traveling to the lighter zone and it is giving you the lighter zone distance, and next to the darker zone it is giving you darker zone distance. In the same way, till the rotation of the shaft is completed, it will give you the signals. Now, this particular section B also, when it is rotating, initially it is covering a larger area than that of the photodetector A, right? The photodetector B is covering the larger area of the light source compared to the A. You can see here the comparison, right? It is covering more amount of the area initially, right? So it is giving you the larger light detector simulation. Next, when it is falling onto the darker zone, it is giving you this particular simulation, and next lighter zone, dark, light. In this way, the signals will be given. So, by this particular signal simulation, we can identify that this particular rotor is rotating in the clockwise direction. Right? This particular signal simulation, we can identify that this particular encoder is rotating in a clockwise direction. In the same way, if this rotor is rotating in an anti-clockwise direction, right? If this particular encoder is rotating in an anti-clockwise direction, how will we identify that it is rotating in an anti-clockwise direction? With the help of this signal processing, as I've told, A, B. Now it is if it is rotating in an anti-clockwise direction, what happens? Here the light source for B will be less, right? Yes or no? The light source for B will be less, whereas for the dark source it is more. Right? For the light source it is less, for the dark source it is more. Again, here it will be in this particular process. Right? Whereas for A, it is more in the light source and less in the dark source. More in the light source and less in the dark source, and this is how we simulate. So, depending upon this pulse simulation, depending upon this signal processing, we can identify by this particular distance simulation, we can identify that the rotor is rotating in an anti-clockwise direction. Right? So here the incremental optical encoder is also used to determine the direction of rotation of the encoder as well as the shaft, rather not only by determining the angle. So the angular displacement by this particular encoder will be calculated by counting the number of light zones and by counting the number of dark zones. That will give you the angular displacement. Clear? Hope you have understood. So this is about the encoder. That is, initially the encoder is used to determine the angular displacement of the robot's manipulator or robot shaft. Right? So with the help of the absolute encoder and with the help of the incremental optical encoder, we will be determining the angular displacement. Since the absolute optical encoder is more complex in design and is more expensive, that particular type of the optical encoder is not much frequently used, whereas the incremental encoder's construction is simpler and it is cost effective. So this is one of the type of the encoder when compared to the absolute, which is frequently used as a feedback component device. Right? As a feedback component device in the robot, we can use the optical encoder system. Right? So, in the absolute encoder, we will be determining the angle with the help of the binary codes, and by calculating the binary with the help of the number of consecutive surface binary codes, we will be getting the angular displacement. Whereas in the incremental optical encoder, by counting the number of light and dark zones, we will be calculating the angular displacement, which can be measured with respect to the known starting position. Right? The angular displacement can be measured with respect to the starting position. Clear? So this is all about today's class about the encoders, and in the next class we will be studying about the various types of encoders. Again, you have the torque encoder systems, the force analysis systems and all. So all that we will be studying in the next class. So signing off for today, Dr. G.
Like, share and subscribe. Hit the bell icon for more updates.